Good morning and welcome to this week's Red Short Seminar. My name is Jim and today I will be discussing machine learning gone bad. As always, you can find information on similar topics at redskyalliance.org. If you have missed any of the previous Red Shorts, you can find them there as well. Machine learning, ML, is an umbrella term for solving problems for which development of algorithms by human programmers would be cost prohibitive. And instead, the problems are solved by helping machines discover their own algorithms without needing explicitly told what to do by human developed algorithms. When there was a vast amount of potential answers, the correct ones need to be labeled as valid by human labelers initially, and human supervision was needed. To make the machine learning model to learn the wrong thing, adversaries can target the model's training data, any foundational models, or both. Adversaries exploit this class of vulnerabilities to influence models using methods such as data and parameter manipulation, which practitioners term poisoning. Poisoning attacks cause the model to incorrectly learn something that the adversary can exploit at a future time. For example, an attacker might use data poisoning techniques to corrupt a supply chain for model designed to classify traffic signs. The attacker could exploit threats to the data by inserting triggers into the training data that can influence future model behavior so that the model misclassifies a stop sign as a speed limit sign when the trigger is present. A supply chain attack is effective when a foundational model is poisoned and then posted for others to download. Models that are poisoned from supply chain type of attacks can still be susceptible to the embedded triggers resulting from the poisoning of the data. Attackers can also manipulate ML systems into doing the wrong thing. This class of vulnerabilities causes a model to perform in an unexpected manner. For instance, attacks can be designed to cause a classification model to misclassify by using an adversarial pattern that implements an evasion attack. Ian Goodfellow, Jonathan Shines, and Christian Segley produced one of the seminal works of research in this area. They added an imperceptible to human adversarial noise pattern to an image, which forces an ML model to misclassify the image. The researchers took an image of a panda that the ML model classified properly, then generated and applied a specific noise pattern to the image. The resulting image appeared to be the same panda to the human observer. However, when this image was classified by the ML model, it produced a prediction result of gibbon, thus causing the model to do the wrong thing. Adversary can cause ML to reveal the wrong thing. In this class of vulnerabilities, an adversary uses an ML model to reveal some aspect of the model or the training data set that the model's creator did not intend to reveal. Adversaries can execute these attacks in several ways. In a model extraction attack, an adversary can create a duplicate of the model that the creator wants to keep private. To execute this attack, the adversary only needs to query a model and observe the outputs. This class of attack is concerning to ML-enabled application interface providers since it can enable a customer to steal the model that enables the API. Defending a machine learning system against an adversary is a hard problem and an area of active research with few proven general solutions. While generalized and proven defenses are rare, adversarial ML research community is hard at work producing specific defenses that can be applied to protect against specific attacks. Developing tests and evaluation guidelines will help practitioners identify flaws in the systems and evaluate prospective defenses. This is an area of research has developed into a race in the adversarial ML research community in which defenses are proposed by one group and then disproved by others using existing or newly developed methods. ML models that successfully defend against attacks are often assumed to be robust, but the robustness of ML models must be proven through test and evaluation. The ML community has started to outline the conditions and methods for performing robustness evaluations on ML models. The first consideration is to define the conditions under which the defense or adversarial evaluation will operate. These conditions should have a stated goal, a realistic set of capabilities your adversary has at its disposal, and an outline of how much knowledge the adversary has of the system. That's it for today. Thanks for joining us. I hope you enjoyed the material and found it useful. If you have any further questions, you can contact me at the email address on the screen. Have a good one, and we'll see you next week.